Okay, so for that shoe brake now we take the third case. Now the fulcrum is at point 3 here, and then it has got, like last time, there is certain direction of rotation. So this is the torque or the speed in this direction. Then it has got a radius r, certain distances are given. This is x and this is y. And the in line with this here, this is A, and from here to here it is B. Now, as we have seen last time, because of the direction of rotation like this, it is going to exert a force, frictional force, in this direction. This is mu F if this is F. So in fact what I have shown, F is acting on the drum by the shoe, and in this direction it is acting. This is the force that is acting on the shoe by the drum. This is the one which is acting on the shoe by the drum because of friction. This is because of normal reaction. So we have to decide the direction of effort. It could be this, and then the usual given things are there. P is given, speed is given, coefficient of friction is there, x, y is there, and what else is required? AB is also there, and you have to find P. Effort P you have to find out. So we say that power P is equal to 2 pi nt by 60 watts. So therefore T is equal to certain Newton meters which you obtain from this equation, because P and N are known. But this T is nothing but, now in this case there is no T1 minus T2. So this T is the braking torque that it is going to be. Whatever torque you are applying, equal and opposite braking torque you are supposed to apply, TB. Now this braking torque is going to come because of frictional force in this direction. So this braking torque is mu F into R. Braking torque is mu F into R. So therefore you can say that F is equal to TB upon mu R. So how much F is required, that value you can find out, because braking torque is same as applied torque, mu and R they are given, so you know how much is the normal reaction you require. So now we will go to the equilibrium of the lever. So for equilibrium of lever, so we have to draw the diagram for the lever, which is like this. This is a lever. At this point, there is a normal reaction that is acting. Force by drum on lever. Then as mu F is acting somewhere here. Fulcrum is here. So both of them, they are causing clockwise movement. Both of them, force and distance, force this distance, clockwise. So to nullify that, you are applying effort in the upward direction, which will cause anti-clockwise movement. So having done this, now you can see that P, now certain distances are there, this is Y, this is X, and from here to here it is B. So you can see that P into Y is equal to, on this side it is F into X plus, right here, mu F into B. So that P is equal to F into X plus mu F into B divided by Y. So all the terms you can see on this side, they are known, because F was just now obtained, A, B, X, Y, B, everything are there, mu also is there. So you can find out how much is the effort you require in newtons to be applied here. If the answer comes negative, then you have to change the direction, but if your assumption is proper, it will not come negative. So that is the effort you have to apply, that is what is asked. So this is the exercise on the third case. So I should write here case 3, where the effort is at this point. Okay, so this is the problem is solved. Earlier we have seen what happens when the fulcrum is here. At that time, this mu F was not creating any movement. Then when we have seen that the fulcrum is at this point, that time mu F was assisting the effort applied. And that has created a situation where by adjusting X and Y, you can get a situation where effort required could be 0. That is a condition of self-locking that was possible when the fulcrum was somewhere here and mu F was below. Then we saw one example also, real life example of a unit which is used for the purpose of lifting the load from some height. And then even if you stop the lifting action, still it will not go down again. Then this was the third case where the fulcrum is at point 3, and then maybe I'll write here case 3, fulcrum at point 3. Fulcrum at 3. And then this is the way you can find out the effort that is applied by hand at this point. Remember, all these forces, they are perpendicular to the lever everywhere. Okay, so that was the third exercise which you can properly note down and understand.